In March 2019, NASA had a working budget line for a nuclear thermal propulsion engine. By December, it didn't. That's the whole story, in a way. 7 months. A program that had survived since the Eisenhower-era NERVA tests, revived under the Game-Changing Development Program, funded again through a partnership with DARPA, and then quietly folded into a budget request that Congress never fully approved. Not canceled with a press release. Just not funded. The kind of death that doesn't make headlines because nobody announces it. Here's why that gap matters more than almost anything else happening in space right now. Nuclear thermal propulsion isn't just a faster engine. It's the difference between a 6-month trip to Mars and a 9-month one. And in orbital mechanics, that 3-month difference changes everything about radiation exposure, food supply, and how much you need to carry. NASA's own 2021 technical reports put the thrust-to-weight advantage at roughly 2 to 3 times that of chemical propulsion for the same fuel mass. That's not an incremental gain. That's the kind of number that decides whether a mission architecture works or doesn't. So America had this: tested components, engineering drawings, a reactor design, the Draco program, run jointly by DARPA and NASA, that got as far as selecting Lockheed Martin and BWXT as contractors in 2023, 4 years after the funding gap. 4 years of essentially restarting. And while that gap sat open, China's space program did something almost mundane by comparison, and that's exactly the point. They didn't build a flashier reactor. They didn't announce a Mars mission with nuclear engines. What they did was take the modular, mass-producible component philosophy, the idea that you build space hardware the way you build cars, on a line, with interchangeable parts, and apply it to something America had only ever built as one-off prototypes: orbital infrastructure modules. I want to be careful here because this is where most videos overstate the case. China does not currently have an operational nuclear thermal engine in space. Neither does anyone. That's not the claim. The claim is narrower and in some ways more interesting. The manufacturing approach America designed and then couldn't afford to scale is the same approach China's commercial space sector borrowed from its EV battery supply chains, and it's now producing satellite buses and station modules at a rate that the U.S. hasn't matched since the Apollo program's peak years. We'll come back to that NERVA to Draco gap because it explains something else, something about why China's October 2024 announcement on Tiangong's expansion modules barely registered in Western coverage when it probably should have. Here's the mechanism, and it starts somewhere you wouldn't expect: a battery factory in Ningde, Fujian Province. CATL, the world's largest EV battery manufacturer, didn't get into space hardware by accident. In 2021, China's State Council folded space manufacturing standards into its broader, new productive forces industrial policy, the same framework that pushed solar panel and EV battery production toward what analysts at the China Aerospace Science and Technology Corporation, CASC, started calling satellite constellations as a manufactured good, rather than satellites as engineering projects. That phrase matters. It's the whole shift in one sentence. What does that actually look like on the ground? Geely, yes, the car company, the one that owns Volvo, built a satellite factory in Taizhou that came online in 2022, designed explicitly using automotive production line logic, standardized chassis, modular payload bays, parts sourced from the same supplier networks that build car components. By 2023, that single facility had a stated production capacity of around 500 satellites per year. For comparison, the entire United States launched roughly 200 satellites total in 2023, across every manufacturer combined. This is the part where I have to slow down because the number itself doesn't mean much without context. 500 satellites a year from one factory isn't about any single satellite being impressive. It's about cost curves. When you build something 500 times using the same jigs, the same suppliers, the same quality control line, the marginal cost of Unit 400 is a fraction of Unit 1. America's traditional space contractors, Lockheed, Northrop, even SpaceX for its non-Starlink work, still largely build in small batches, with bespoke engineering on major components. SpaceX is the exception that proves the rule, and even SpaceX's Starlink line, impressive as it is, was modeled in part on observing exactly this kind of automotive-style production logic. Now here's where it connects back to that nuclear propulsion gap from Part 1, and I promised we'd come back to it. The Draco reactor program wasn't just about the engine. Buried in the 2019 to 2021 technical proposals was a secondary goal, developing standardized reactor modules that could be mass-produced for multiple mission types: Mars transit vehicles, lunar surface power, deep space tugs. The engineering term in NASA's own documents was Common Bus Architecture. It's the same underlying idea as Geely's satellite chassis. Build one well-tested core, then adapt the payload around it, over and over, at scale. America designed that philosophy. Then the funding gap hit. The program shrank to a single experimental demonstration. Draco's planned 2027 test flight is now just one reactor, one spacecraft, no production line behind it. And the broader manufacturing lesson never got applied beyond that one program. China, meanwhile, never built a nuclear reactor for space. But they took the manufacturing logic, modular, line-produced, supply chain integrated, and applied it everywhere else: satellite buses, station modules, and increasingly, the docking and life support components for Tiangong's expansion. The October 2024 announcement I mentioned wasn't about a single new module. It was about CASC confirming that future Tiangong expansion modules would use a standardized docking and power interface across multiple module types, explicitly citing reduced unit production time as the justification. That's the quiet part, not a breakthrough, a production decision. And production decisions over a decade beat breakthroughs that never get a second unit. Now, the obvious pushback, and I want to give it real weight because it's not wrong on its face. Volume isn't capability. China can produce 500 satellite buses a year, but a lot of those are small communications or remote sensing satellites, not the kind of high-reliability, radiation-hardened, decade-plus lifespan systems that deep space missions require. NASA's Perseverance rover, for context, was built with components tested against failure modes that simply don't show up in a 4-year LEO communications satellite. Building a lot of something isn't the same as building the hard version of something. And on nuclear propulsion specifically, China hasn't demonstrated anything. No ground test of a space reactor, no equivalent to the kilo-power reactor NASA tested at the Nevada National Security Site back in 2018, which actually ran for 28 hours at full power and proved the basic physics worked at small scale. So if the comparison is who's closer to a nuclear-powered Mars mission, the honest answer is probably still the United States, on raw technical capability, even after the Draco gap. But here's the reversal, and it's the thing that took me a while to actually sit with. The question was never who builds the better reactor. The question is, who can build 40 of whatever wins, fast enough, cheap enough, to actually run a sustained program? And that's a manufacturing question, not a physics question. America's space industrial base, even today, is structured around big, expensive, one-off systems with 5 to 10-year development cycles. The James Webb Space Telescope took over 20 years and ran roughly 10 times over its original budget estimate, not because the physics was uniquely hard, but because almost nothing about how it was built was repeatable. Every component was bespoke. China's approach, inherited from E5 batteries, from solar panels, from the entire New Productive Forces push, assumes from day one that you'll need many units and designs the production line before you've even finalized which mission needs them most. That's backwards from how America has traditionally built space hardware. And it's also, uncomfortably, closer to how America itself built things during the periods historians actually point to as peak space capability, the assembly line production of Apollo-era Saturn V components, where multiple rockets were genuinely in production simultaneously, not built one at a time. So the irony, and I think this is the part that should sit uneasily, is that China didn't invent this approach. It relearned an approach America used 60 years ago, abandoned for decades, briefly tried to revive through programs like Draco's Common Bus architecture, and then defunded again in 2019 before the lesson could spread beyond one experimental reactor. I'm not certain how this plays out over the next decade. The data tilts toward China closing the production gap faster than the US closes the manufacturing philosophy gap. But Draco's 2027 test, if it goes well, could restart exactly the kind of institutional momentum that got cut in 2019. Programs have come back from worse positions. What I am fairly confident about is this. The conversation about the US-China space competition keeps framing it as a race between specific technologies. Whose rocket, whose reactor, whose rover. That's the wrong unit of analysis. The actual race is between two theories of how you build things at all. So let's close the loop properly. In March 2019, NASA had funding for a program built on an idea: standardized, mass-producible space hardware with nuclear propulsion as the proof case. By December, the funding was gone, but the idea wasn't dead. It just got narrowed down to a single experimental reactor, scheduled for a single test flight in 2027. One unit, no line behind it. China never touched that program, never needed to. The idea, modular, line-produced, supply chain integrated hardware, was already sitting in CASC's industrial policy documents, borrowed wholesale from how the country had already learned to build EV batteries and solar panels at a scale nobody else could match. They applied it to satellites first because that was easiest, then station modules. The October 2024 Tiangong announcement wasn't a leap forward. It was the philosophy finally reaching the part of the program where it actually matters. Here's my honest read on what this means, and I'll say it plainly. America didn't lose this because of a worse reactor design, a smaller budget in absolute terms, or even less talent. NASA's FY 2024 budget, roughly $25 billion, still dwarfs CASC's estimated annual spend. America lost the manufacturing argument in 2019, in a budget meeting most people have never heard of, and hasn't fully had that argument again since. My prediction, and I'll stake something on this, is that Draco's 2027 test flight, whatever its result, won't be the thing that determines this. Even a perfect test produces one reactor. The real signal to watch is whether anyone in Washington, after that test, asks for funding to build the 10th one before the 9th even exists. If that conversation happens, the gap closes. If the test succeeds and the program quietly returns to single-unit funding again, the way Draco itself emerged from a canceled predecessor, then the gap doesn't close. It just moves. China, for its part, doesn't need a moment like that. The production line is already the point. It was the point before anyone decided what would roll off it. 7 months in 2019 between a program existing and not existing. China didn't need 7 months. They needed a battery factory that already knew how to do this, and a state planning document that told it to. If you've ever wondered why America still leads in space technology and China is closing the gap faster than expected, can both be true at the same time. This is why. They're not measuring the same thing. That's where I'll leave it. If this kind of structural red, the stuff underneath the headlines, is useful to you, there's more of it where this came from.